All right, everyone, welcome to the inaugural New York C Meetup. I'm so happy to see all of you. Thank you so much for coming. I thank you so much. Someone knows when I'm fishing for an applause break. Uh, I want to introduce you to Dan Katz. He is the lifeblood of this group. He has really carried this meeting on his shoulders. Thank you so much for making this possible. Everyone, Dan Katz.
Thanks, Nick. Oh man, I got a mic and everything. This is nuts. Welcome everyone to the inaugural NYC Meetup, the only possible name for this event. It is low-hanging fruit, but it is good fruit. My name is Daniel Katz. I'm a senior software engineer from over at Bloomberg, and I think it has been a little while since we've had an event like this in New York City for the C++ community. Some of you might remember that for several years, MongoDB hosted an awesome series of C++ meetups. I attended several of them myself, a lot of exciting speakers, a lot of great talks. I'm sure some of you also attended. And I think if we succeed with what we're trying to do here tonight and into the next several months ahead and like really get a series of meetups going, we're hoping for this to be a sort of spiritual successor to those past events. So the idea for these events started a few months ago over at Bloomberg. Me and Brett Brown just kind of like started running with the idea, and we started pulling in friends and colleagues from other firms. Kristen Shaker from Alphabet, she pulled in Margot Liebold from Meta. Of course, David Sankel from here at Adobe, and he pulled in Nick DeMarco, my fellow co-organizer for these meetups. And we just found that everyone we were talking to was just like, yeah, let's get a bunch of companies together and like fund a series of C++ meetups, and like we'll rotate on kind of who's hosting each month. And everyone was just psyched to make it happen. Everyone was really excited about it. But I do want to acknowledge we're still kind of like getting situated with being able to accept donations from different companies to, sustain this financially in the longer term. So for today, the only reason why we are able to be in this room together and have these wonderful Alidoro sandwiches is because Adobe offered to sponsor this whole event single-handedly, and not just sponsor, but lend us this wonderful space that we're all able to be here in. So I just want to thank Adobe for their generosity, for their commitment and investment in the New York C++ community, and I really think we should just give them a round of applause. So yeah, I am really excited to be up here. I'm psyched that this was able to happen, come together. I'm excited to just like address such an awesome community of engineers. And of course, I'm excited to introduce David Sankel, tonight's invited speaker. And some of you might already know David. Maybe you work with him now at Adobe. Maybe you had the pleasure of working with him during his tenure at Bloomberg, or maybe you've been lucky enough to see him talk at CPPCon or C++ Now, or one of the other conferences he's been invited to speak at. David's been a prolific member of the C++ community for many years now, and I think not just in New York, but internationally. And so I think it's pretty amazing that we're going to have the opportunity to hear him talk, in what's basically a lot of our backyards, right? Like Manhattan, we're right in Midtown. And the reason I bring this up is because, I think it's kind of what makes local community meetups so awesome and special. Maybe not in contrast, but complementary to larger international conferences, right? It brings us together into the same room. It lets us network, exchange ideas. I can talk to you about all the weird problems I'm having with C++, and I can listen to you tell the same to me. We get the chance to hear like these like people who are right at the vanguard of our discipline talk and present. It's also more accessible. It's accessible to students. It's accessible to people learning the language for the first time, to people who are maybe coming back to the language after many years away. We can get together more often, right? We can get together more than these 3 or 4 conferences per year. And maybe most importantly, to get together, we don't have to convince our employers to foot the bill for us to travel to Colorado or to Toronto or to Kona or to Issaquah. And I think our hope is also that if we spend a little bit more time in meetups like this, a little more time talking to each other in the same room, maybe some of the ideas that we have, the technical direction of the language, maybe they'll start to get a little bit more convergent, right? Maybe we'll maybe our ideas around like our libraries ecosystem, our tooling ecosystem, build and packaging opinions, maybe those will just become a little bit more similar. And for my part, I think that would probably be a really good thing for the community. So that is what this is about. That's what we're trying to do. I'm going to ask you all, please keep an eye on our meetup page in the weeks ahead. We're hopefully going to have another event coming together for December with another exciting invited speaker. And we're just going to keep trying to keep it going from there. We will have news coming soon about how any companies that want to try to support what it is we're doing financially can do so and just try to make this sustainable in the long term. But maybe even more importantly, if any of your employers you think would be interested in hosting a meetup like Adobe has done for us here today, right? Whether it's opening your offices to share that space with us or whether it's hosting something off-site, it doesn't have to be like, 50, 60, 70 people. It can be less, can be more. Please reach out to us. The more companies we have involved in the hosting of this, the more we can rotate between, the easier it's going to be to maintain a cadence of like, a meetup every month or 2 meetups a month. And we would love to see that happen. It's a great branding opportunity. It is an awesome opportunity for your firm to advertise itself as a first-class employer of C++ talent in New York City. And it's a great way to just get prospective talent into your offices, experience something about like your company culture and what it would be like to work there. So, talk to me today while we're all here, or reach out to me on the meetup.com group. But let's try to keep this going. So that's enough talk about the meetup. Let's hear more about C++. So it is my pleasure to introduce David Sankel, principal scientist here at Adobe, chair of the Boost Foundation, who's going to talk to us about the semicolon, which we all thought we know so well from our very first Hello World, and why it is not what it pretends to be.
Thanks, Dan. How's everyone doing tonight? Good? Yeah, you just got fed. It's good. All right, so yeah, the name of this talk is Semicolon is a Lie, and like a few people were speculating about what that means before, and they started getting a little bit close to it, and I was like, shh. Like, don't give it away. All right, we're going to talk about a few different things. That's just one of them. So anyway, this is an outline of this talk. So we're going to talk about David's computer history. That's me. I'm David. And that starts in about 1980-ish era when I'm born, and there are a few points there. And then we're going to talk about programming history, which happened a little bit before I came around. And then they intersected at that point right there when I started programming C++. And then there are a few things that happened after that. But in talking about this history, we're going to cover Grace Hopper's compiler. We're going to talk about the C programming language, C++ programming language, second edition, and then birth of David. That's me. That's when I got a 386 SX computer. And then this is when I started programming C++ on a Pentium. And then we're going to go into the future, and we're going to talk about IOU ring. How this stuff gets pulled together, I have no idea. We'll see if we can make this work. But I'll give you my thesis right now. Number one, computers are fast. Maybe you didn't need to be convinced of that, but I'll convince you even more. Number two, programming is an illusion. And number three, IOU ring is the future. Okay, this will make more sense as we go on. It's all right. This is the first computer that I programmed on. This is the TI-99-4A. And I was probably about 5 years old, and my parents bought this thing, and both my mom and my dad would be on this thing a lot, programming it. And the way that you use these things is you would buy like a book or a magazine, and you would open it up, and it would have all this code in there, right? And this is basic code. And they would sit there, and they would type in this basic code, and then run the game or whatever. And from my perspective as a kid, it was really annoying because all that I saw on that screen, for the most part, were my parents typing in code. And all I wanted to do was play the game, and they would assure me like, no, we've got to do this, and then later we can play the game. And I wonder if they just kind of gave up at some point, and just, because I never got to play the game. But anyway, that's what it was. So this particular computer had 16 kilobytes of RAM, 16-bit registers, and was 3 megahertz. Now, one of the things I want to do is build an appreciation for computers and like how fast they are. So to do this, I'm trying to build some imagery so we can get a feeling like based on everyday life, what that means. So first, 16 kilobytes of RAM. I have this book at home and it's like extremely dense. And I went through and I counted every single character on these pages. And basically 16 kilobytes of RAM is 2.65 pages of this book, right? These 2 pages and maybe like, you know, a little bit of the next page. That's how much 16 kilobytes of RAM is. Not a lot you can do with that RAM. And then they had this expansion kit that you could get for this device, but I didn't have that. My parents couldn't afford that. But that would give you 23 kilobytes in addition to the 16 kilobytes, giving you a grand total of 8 pages of this book. So what about the speed? Okay, 16-bit registers, 3 megahertz. What do you do with that? So I was able to look up and find the TMS 9900 microprocessor data manual. Okay, and this tells us how these instructions work. And so our basis of comparison is going to be the add instruction. So how long did it take to add? And you're not going to be able to read this, but basically it gives a formula here that tells you that the amount of time it takes for any given instruction is equal to 1 over the clock rate, basically the duration of the clock, times the amount of clocks required for the instruction plus W times the number of memory accesses times the amount of memory clocks required for that instruction, okay? And down here we have the add instruction, which is just A in this assembly language. And it takes 14 clock cycles and it uses 4 memory accesses for every memory access required to execute that instruction, right? So we put this together, 1 divided by 3 million, which is your 3 megahertz, times 14 plus 0 times 4. So 14 clock speed, and then the 0 times 4, I'm just doing 2 registers added together. Does everybody know what a register is? If anybody doesn't know what a register is, like raise your hand. I'm happy to explain it. But anyway, T comes out to point some number of zeros for 7 seconds, which is 4.7 microseconds. Now, I don't understand what 4.7 microseconds is. I mean, I understand like a half second, I understand a few seconds, but 4.7 microseconds, that's not something I can fathom. But what I do know is that I have a daughter and she can do arithmetic. And so what I did is I had her sit down and add 2 16-bit numbers, right, by hand. And it took her 18 seconds. This is my daughter, Carmen. Okay, so now we know how long it takes my daughter, Carmen, to do 16-bit arithmetic. How long did it take the computer? Well, how much faster was the computer? Well, it turns out that the TI 994A is 3,829,787 times faster. So so just think about that. In the time it takes my daughter Carmen to add 2 16-bit numbers, this machine, this is an old machine, can do it 3.8 million times. That is crazy. I think it's crazy. So anyway, let's move forward into the future. Now we're over in like almost 1990. This is when I got to mess with a 386 SX. The other computer, they didn't really let me touch unless there was a game on there. This one, I went in there, I put in disks, I messed with DOS, and ran games. I didn't do any programming, I was too young. But anyway, this has 4 megabytes of RAM, 40 megabyte hard drive, 16 megahertz, and 16-bit registers. So, 4 megabytes of RAM, that's 1 book. That's about 600 and something pages of a book that size. That's 4 megabytes. Obviously, you can do a lot more with 4 megabytes of RAM. This is how much 40 megabytes of the hard drive space is. It's basically about 10 books. If my son Steven is sitting there, it's almost hitting like his eye level number of books. That's how much we were able to store on the hard drive back then. Now, what about this add here? Wait, the 386, no, 386 was 32 32-bit. Yeah, sorry, that was a mistake on the previous slide. The rest of the slides are doing it correctly. Okay, but the add took 3 clock cycles with this computer, and that comes out to 0.1875 microseconds or 187.5 nanoseconds. So let's do a comparison. I got Carmen's older sister. Okay, this is the upgraded model of the Sankel family. And I had her do 32-bit arithmetic. And she was able to clock that in 19 seconds, which is impressive, right? Because Carmen was able to do 16-bit at 18 seconds, so she only took like an extra second to do 32-bit, so that's pretty amazing. So how much faster is the 386SX? Well, it's 101,333,000 something times faster. Okay, it's really fast. Why do people say computers are slow? Like that? All right, moving forward a little bit. Now we get to David doing C++ on a Pentium, okay? Fancy, and that's me doing C++ on a Pentium. I don't know why I had that earpiece in. Like there was no video conferencing. But for those of you who were around back then, you'll notice that this is, I think it was called a quick cam, a little black and white camera. It was very fancy back in the day. So anyway, this is a Gateway 2000 computer, which I'm sure many of you have never heard of, but it was all the rage back in the day. And this had 16 megabytes of RAM, which is 4 books, 500 megabyte hard drive, which is 125 books. That's more books than I have in my house, and I've got a lot of books. And 133 megahertz with a 1-cycle addition. And essentially, when it comes down to it, this is 2,537,000,000 times faster than Christina is at adding numbers. So really fast. Okay, so that's enough about me. Let's go way back in time, all the way to, so this is 1940, 1960, so this is probably like the late 1940s. But before we do that, I want to talk about what a semicolon is, okay? This is a real dictionary. Like, I'm going retro here. Semicolon, a mark of punctuation indicating a greater degree of separation than the comma. That's pretty cool. You know, I didn't realize that it was tied to the comma, but if you think about C and C++ and the comma operator and the semicolon operator, it kind of makes sense. You know, the comma is a little bit less of a separation than a semicolon. Anyway, we'll come back to this later. So in 1947, this is when assembly language first came on the scene. All right, so there's this lady, Kathleen Booth, you see her on the left there. She took this, she was making a notation for this ARC machine that she was making with her husband on the right there. His name was Andrew Booth. And so basically they came up with these instructions. You sequence the instructions, a different instruction on every line, and each one of these instructions would correspond to the machine code that you would put into this ARC machine. And in the really early document, they had this to say, the advantage of this arrangement is obvious. We shall be able to transfer any problem which has been coded for ARC directly to the electronic machine when this becomes available. Now, what she's talking about there is they made the ARC and it had like drums and like some weird machinery, and they were working on a new computer, which was going to be an electronic computer. And the idea was they can write some programs for the ARC and then be able to use those programs on the new machine, even if it has a different machine code, right? So the whole idea at the very beginning here was just kind of portability. And then it also says, in addition, the experience which we gained from using the simpler machine may form a valuable guide to possibly advantageous modifications of the code for the faster computer. So again, you like use the simple one, be able to use it on the more complex one. All right. What else? Okay, now we have Corrado Bohm, okay? And this guy, what he did is he made a compiler as part of his thesis, but it was like a theoretical compiler. It wasn't a real compiler. He invented this language. And the compiler for the compiler, the compiler for the language was written in the language itself, which was also kind of an innovative idea. But he had this compiler for this theoretical machine, which he also produced in this document. And his rationale is here. He said, The human must then transform each phase of the computation into a sequence of operations that can be executed by the machine. So he's talking about when you have a programming problem. Back then, you'd have to think about it, you'd come up with a solution, but then there's this extra step to encode it into the machine. And he said, but to what extent could the machine even compute the sequence for itself, starting from certain formulas that express the method for solving the proposed problem? The answer is the principled goal of the present report. Below, for brevity, we refer to this question as automatic programming, right? So before, when you were doing machine code, they were calling that programming. Now it's automatic programming because something else is doing the programming for you. You write in some other thing, and then that does the programming of the machine. So it's pretty cool. But mostly they're concerned here, when you read this document, he's mostly concerned with the time on the machine, because people spend so much time on the machine debugging their incorrect translations of whatever their thought is, and machines are very expensive and time is like hard to get on a machine. He's like, hey, you don't have to have as much time on the machine, which I thought was pretty interesting. And so very soon after 1951, you've got Grace Hopper, whom you've probably heard that name before. There's like this famous conference named after her, but she made the first actual compiler in practice. So what she did is she basically made a compiler for this A0 system, this like arithmetic language version 0 system. And her main concern was, I think, similar to the other ones, but in essence, it was a very primitive compiler. It was almost more like a linker than a compiler, but she had the basic idea here. And she was actually quite influential in programming language thought, because she kept on pushing hard for this idea of, hey, we should be programming these things in human language. And that's eventually where COBOL fell out of that. And that's a language I'm sure most of you have heard of. All right, so everything is going just fine in the history of computing until Fortran. So then this guy, John Backus, said he wanted to make a more practical alternative to assembly language for the IBM 704 mainframe computer, which you see a picture of on the right here. And this was the first optimizing compiler. And what I mean by optimizing is the code that you write in the language, as a reader, you're not going to be able to predict what it's going to create in assembly or in machine language, because it's going to do all kinds of crazy stuff. So he kind of ruined the semicolon right then, way back in the day. And why did he do this? He did it because he said it was our belief that if Fortran during its first months were to translate any reasonable scientific source program into an object program only half as fast as its hand-coded counterpart, the acceptance of our system would be in serious danger. He did it because he was scared that if it didn't optimize, then people would say, this is ridiculous, we're not buying it. And this was a pretty significant investment. Was it IBM that made this? I think it was IBM, not sure. But it took 16 engineer years to make the first Fortran compiler. So that's like a huge investment, and they wanted to make sure that it was going to be used, so they made it fast enough, and they ruined the semicolon. So the way that he broke this, so if you have A equals 1 semicolon, B equals 1 semicolon, since him, it no longer necessarily produces what you would expect in the assembly language, like moving 1 into the RAX register, moving 1 into the RBX register. Over right then. Okay, but then things got even worse. So we've got Frances Allen, who is one of the pioneers of program optimization. So she introduced graph data structures to encode program content for optimization. She produced this work. It talked about loop unrolling, fusion, redundant subexpression elimination, dead code elimination, instruction scheduling, all this stuff. It all like became out there with her work, and she collaborated with others. And the idea that you can take your source language and understand what's going on in the assembly is just, it's like completely disappeared. Now it's enshrined in the system that this is how compilers work. All right, I mean, I'm being too harsh. They did wonderful things. I mean, this is great. But I mean, I don't know, maybe computers were too slow back then and they needed this. So moving forward, we have C. So here we have Dennis Ritchie and Ken Thompson. I don't know which is which. Didn't say, there wasn't a caption. But what happened here is Ken Thompson was trying to write a language for this Unix operating system. And he started by saying, well, let me try writing a Fortran compiler. And apparently he just gave up on that. He was just like, oh my gosh, no, can't do it. So he made a language called B, I believe. And then Dennis Ritchie tried this on this PDP-11, I think, and it was too slow, and he added enhancements, and he turned it into the C programming language, which we all know today. And it took him 1 year working on this to create a C compiler, like just 1 year for the initial C compiler, which I think is pretty impressive. But the idea was to make this for this Unix operating system. Particularly, it was for the utilities to write in Unix. So like, I don't know what Unix utilities, LS, I don't know what they did back then. But then they liked it, so they rewrote the kernel, which was originally written in an assembler, in C, and now like C is everywhere, and we all know about that. All right, now we move forward a little bit further in time, and we get to C with classes, which came out in, I don't know, close to 1980, a little bit before I was born. So Bjarne Stroustrup, who's here, welcome Bjarne. He did this, and he basically said, and please correct me if I'm wrong, that Simula is nice, it's got some nice features, but it's too slow, right? So Simula had some higher level features like classes and things along those lines that you can use to make bigger systems, but it was too slow to be practical. But then there was also BCPL, which was very fast, but that was too low level. So what he did is he took C and started adding some Simula features like classes to it, and started building a programming language that was like C, but was more scalable with larger systems. A little bit later on, we have the C++ programming language first edition, and then we've got the C++ programming language second edition. 2 computers, that's pretty sweet. And moving a little bit forward, now we're back to where I am. I'm programming C++ on a Pentium. And C++ at that time, at least at that period, I'm probably one of the first of the generation that actually had computers at home when they were growing up. But at this time, we didn't talk about assembly. Like when I learned how to program on the internet, there was this thing, yeah, we knew that it existed, but nobody really seemed to be learning assembly at this time. You would just learn your programming language, and then it would make executables. And you didn't really care about what was going on in between. And I tried to get Visual Studio installed on this Windows 95 box. Had a lot of trouble, probably because it was pirated. But what I eventually did is I figured out how to install Linux on this thing. So my first actual C++ compiler was Slackware Linux G++. And I was so happy when I got my first C++ program going. It was great. All right. Another thing that they didn't do at this time apparently was ergonomics. Like, look at the ergonomics of my setup. My back, like, what am I even doing with that chair, right? And my mouse is like higher than my keyboard. It's like a miracle I didn't come out twisted. But anyway, moving forward in time. Now we're in, I don't know, 2006 era. This is when Pentium 4 came out and did a lot of stuff. So Pentium 4 became 64 bits during this time period, and it used what was called the NetBurst architecture, like whatever that means. We're going to talk about it. So I have a computer today that's based on this. It's probably about 10 years old, and it's called a Z600. Okay, it's an HP machine, pretty high end, but I got it used because I can't afford a high end machine for home. So anyway, this has 64 gigabytes of RAM, which is 6,000 books. Like, that's a lot of books. And a 1 terabyte hard drive, which is 250,000 books. And just to give you like a point of reference, the Library of Congress has about 160 million books. So maybe we're getting close to the point to where we're going to start talking about like how many libraries of Congress can you fit on your hard drive. This has a 2.67 gigahertz CPU, 2 CPUs. There's 6 cores each, and then 12 threads, because each of them has the 2 threads with hyperthreading. So how fast is this? Well, for this one, I got out my oldest daughter. Okay, this is the most upgraded Sankel we've got in our house. Okay, she's 15, Sarah, and I had her add two 64-bit numbers. This took 27 seconds, which is still pretty impressive compared to Christina, considering she's doing a 64-bit addition. She only added a few seconds to that. So anybody want to guess how much faster the Z600 is? Did she get it right? Good question. I didn't check. I don't know if the computer gets it right either. I'm told. Yeah. So I'll tell you the answer. It is 72 billion, 90 million times faster. Okay? Wow, computers are fast. But actually I lied, because that's only one core, one thread. If I add in the fact that it can do a bunch of these things at the same time with multiple cores, multiple threads, the Z600 is actually 1,730,160,000,000 times faster than Sarah. All right, well, computers win, right? Handily. But there was more weird stuff that happened at this time with these machines. And we're going to look at this net burst thing. All right, so we've got some C++ code on the left. We've got some assembly code on the right. We're going to go through it. Don't fret. I'll explain what it means. All right, the first thing to notice is what this C++ programming is doing in this inner loop here. It's saying P1 of I plus P2 of I. Okay, basically you have these two long arrays. You add them together, at each index, and then you add the result of that addition to some kind of like accumulator, A1, right? So you have these two long arrays, and you're basically summing it all together by going to each index in each array. All right, does that make sense so far? Not too bad. Now, you might think, well, that's weird, right? That is kind of weird. Basically, what this is doing is if you're using the Clang compiler, it's going to insert a comment into the generated assembly code. And it's LLVM-MCA. So MCA, LLVM-MCA is a tool that you can get with Clang, with LLVM, which stands for Machine Code Analyzer. So you can really understand what's going on with this assembly. And we're going to be using that. That's why we injected those comments. This is basically saying, I care about what's in between these comments when we talk about the Machine Code Analyzer. All right, now on the right, we see, oh, it generated those comments. Good, that's what we expect. And then we have the assembly code, right? So move into register RCX, which is a 64-bit register, this memory address, okay? So that first line there is basically saying, grab me the element out of P1 and put it into register RCX. The second line says, add into RCX, what I already put in RCX, this other memory address, which is essentially the P2 of I. And then the third thing is to add RCX into this other memory element. So we're adding the register to someplace in memory. That's the A1, that's the accumulator here, right? So it's a pretty straightforward representation of what happens in assembly there. The rest of it doesn't really matter. It's dealing with the loop. We don't care about that. But we essentially have these three instructions. So net burst. I'm going to explain. So this is the timeline view that you get from the machine code analyzer. And we'll talk about it. But basically, you see the same three instructions over there on the right, right? But we see them over and over again, because this is showing what's going on inside of that loop at every single iteration. Now, what you see on the top are different clocks. So clock 0, clock 1, clock 2. So at every single clock, we see what's happening with regard to these assembly instructions. Okay, D says the instruction got dispatched. I have no idea what that means. It doesn't matter. And then we have lowercase e. Lowercase e says that that instruction is executing. Okay? And then the capital E is that the instruction has been executed. All right? So we have the first instruction is executing, and now we have the second instruction. Now what you'll see, which is interesting, is that the second instruction starts executing before the first instruction finishes executing. Right? That's kind of weird. But you might think, okay, so the machine is basically saying, oh, I see that like after I do this move into RCX, then I need to grab this memory from somewhere else. So use a few clocks to start preloading that stuff in memory and then add it to the other one, okay? Pretty fancy stuff, but it gets weirder. Over here, we have the next iteration, okay? We're in the second iteration of the loop, and it starts executing before RCX, the first RCX completed, okay? The problem, the thing that makes this really weird, is that they're both using RCX. This is moving something into RCX while this one is moving something into RCX. What's going on here? The thing that's happening is that these registers are a figment of our imagination. Registers, when it comes to assembly code, they're kind of like hints to the machine, and the machine will allocate an actual register, some like shadow register, which is using in order to be able to get more parallel computation to get computers faster, as if we needed them to get faster. That's what's happening. This blows my mind. So registers are an illusion. Okay, where are we? For speed, of all things, your C++ code doesn't generate the assembly that you expect. Okay, the semicolon's a lie. Thanks, John Backus and Francis Allen, for that. And your assembly doesn't generate the machine behavior that you expect. The new line is a lie. Thanks, Intel. So it's basically illusions all the way down. But the question remains, so what's next, okay? What is that next dot? We're going to talk about IOU ring. All right, but before we do that, we're going to talk about a short history of asynchronous computation in the Linux kernel. So basically, you start with your blocking read and write. You read from the network, it blocks until it completes. Right, that didn't work out, too slow. So they created select. So select is an API call you can use, and you pass a bunch of different file descriptors. Like let's say you're connected to 2 servers, and you select and you say whichever one brings the data back first, give me that one, right? Okay, so now we have some asynchronous computation going on. And then they made epoll, which is the next generation. Epoll, you register all the handlers at once, and then you can reuse them. And it's kind of complicated. I won't go into the detail, but it just made things faster, but it's still the same semantic model. It's just kind of like you're prepping the machine before you do this select operation. And then there was Linux AIO, because all this stuff didn't work with your file system, right? You wouldn't use this for disks. And so Linux AIO was created because they wanted to replace threaded disk I/O. Before Linux AIO, everyone would just spin up a separate thread, and that's where they would do all their block operations. And the reason that they needed this is because high-performance SSD reads, like these new really high-performance SSD drives, they read as fast as a thread context switch. So we're talking single-digit microseconds. It wouldn't work with this threaded method. So we needed to do something faster, and that's where Linux AIO came from. This was specific to database people. It wasn't really used outside of that group, and it notably didn't use the Linux cache. So if you read a file from disk twice with Linux AIO, you're reading it off the disk twice. You're not reading like a cache in memory or anything like that. It didn't work. So Linus Torvalds had some stuff to say about Linux AIO. He wasn't a big fan. So here's what he said. I love his quotes. So I think this is ridiculously ugly. AIO is a horrible ad hoc design with the main excuse being other less gifted people made that design, and we are implementing it for compatibility because of database people who seldom have any shred of taste actually use it. I can't make this stuff up. That's what he said. So someone came to the rescue, this guy Jens Aksobi, and he created IOU ring. And he designed this as an elegant solution to asynchronous I/O on Linux. And this was released with Linux in 2019. So just a couple of years ago, this is a new technology. And I'm going to give you the basic idea for how this works. You start by having a submission queue and a completion queue. Let's say you want to do a couple operations. You want to do a write to file descriptor 1, a read from file descriptor 2. You basically put those two things on the submission queue, and then you say, go, submit, okay? When you say submit, then the stack pointer gets moved up, and now the system does its thing, right? So one system call, two asynchronous operations. That in itself is a pretty big advancement in speed. And then you wait, and some things show up on the completion queue. So here we have FD1 write was done, FD2 read was done, and what you say is, I've seen these, and then the stack pointer moves, and this gets reclaimed. This memory can be used again by the system. Okay, pretty basic ring strategy, but it's incredibly fast, incredibly fast. So there are some really advanced things that you can do with this. You can have dependencies. You can say, I don't want to write, I want to write FD1 after I read FD2. You put that little computation in there and you say, send it, and it will do this one before this one. You're essentially building a little graph of computation for the system to execute. You can do timers. You can say, okay, wait 10 seconds, then write this. Other stuff, cancellation. So here is a pretty interesting one, and I apologize if you can't read that in the back, but basically we have 4 different events here. This one says read server 1, and this one says cancel C, okay, where C is this read server 2. This one says read server 2, and then D says cancel A. What is this doing? It's basically saying, try to read from server 1 and try to read from server 2 at the same time. Whichever one finishes first, cancel the other one. And it'll do that. So in the completion queue, here's an example of something like a possible output. A is successful, which is the one that reads from server 1, which means that B is successful, which means it was able to cancel the other read. And C is canceled, it comes back as canceled, and D comes back canceled. Okay, and this is just really interesting, a really interesting phenomenon because, well, first, it's cool because it handles partial reads elegantly. Like if you cancel something and it read something partially, you can get the partial data if you need that. Cancellation can fail, which is an interesting concept. I hadn't heard of that until I read about this. Essentially, if I try to cancel something that already completed, then my cancel event failed. I failed to cancel that because it already completed, and you get that feedback later on. Everything that goes into this thing, you get something in the completion queue. And what we're seeing in the Linux kernel is they keep on adding more and more system calls to this thing, where almost every single system call that you'd want to do seems like it's going to end up in this IOU ring thing. So looking ahead, I have a couple questions. What if my compiler was, not were, IOU ring aware? What if my compiler saw a bunch of system calls and said, I can execute these in an asynchronous batch to get a little bit more speed because computers aren't fast enough, while maintaining the illusion of the semicolon, right? You still look at it as a normal programmer and it just happens to execute faster because the system calls got batched up together. Interesting. Is there a possibility of doing speculative execution of system calls? Like okay, everybody knows about Spectre. Set that aside for a second. But imagine if you have like a condition, if this is true, then go ahead and read this data off of a disk, and your computer says, well, I know that's probably going to be true, and they're going to need that later on. So let me go ahead and start reading from the disk way up here, so it'll be available when we get down here. Now, what I'm talking about is nothing different from the crazy stuff that's going on in the CPU itself, or the crazy stuff that's going on in the compiler. when it creates the machine language. This is just the next level, is bringing it to system calls even. I don't know. So the second question is, what would a future C++ look like that acknowledges the reality of pipeline and asynchronity everywhere? Like, if this becomes a thing, and this is the new way that we interact with our systems, do we need some way to think about cancellations and failures in this kind of like batched asynchronous underneath the hood way? I don't know. I have no answers. I'm just seeing the trajectory, right? Okay, so we're going to go back and talk about the thesis. Computers are fast, programming is an illusion, and IOU ring is the future. Now, I have some resources that I'm going to point you to now. If you're interested in historical documents, these ones are really interesting. So the Fortran 1 compiler, this is the document that explains the motivations for creating optimizations in the first Fortran compiler. That's where I got that from. The Booth paper, Coding for Arc, this is the introduction of assembly language. It's just really neat to get in the heads of the people that invented this stuff way back then. So if you're interested in that, there's that 1947 paper. The first introduction of a compiler, this thesis is really interesting and got translated into English from French, so you can actually read this and check it out. And then you have a catalog of optimizing translations by Francis Allen and John Cook. It's so funny because in 1971, they pretty much talk about most of the compiler optimizations that we still talk about today. Like, not a lot new has actually happened in that space, at least that's widely talked about. If you're into modern stuff, here's some resources. Modern x64 assembly language. This is a series of videos online that explain how assembly language works, x64 assembly language, and they're fantastic. If you want to learn it, I highly recommend this. I enjoy it. This is what I do for fun at night. And then there's this other website by Agner Fogg, who is, I think he's not even like a programmer. He does something with environmental research. But on the side, he does all kinds of assembly stuff, and he compiled a huge amount of resources to tell you like how many clocks per instruction and the different architectures and what that is. If you're into IOU ring and you want to find out more about that, which I would recommend because it's, I think it's going to have a pretty big splash. There are these two articles written by the creator. One is introducing IOU ring, and the other one's what's new with IOU ring. So this is some of the additions they added, like cancellation and such. And then finally, if you want to learn more about how your CPU works under the hood in order to be able to squeak out the last little bit of performance, I highly recommend this book by Fedor. I started reading this book because I saw Fedor give some talks at conferences, and I was really impressed with what he had. And this book is really cool. So I recommend those. That's it. So now we'll open up to comments and questions. And I'll be repeating your comments and questions so we can have it for the recording. All right. Well, Bjarne? So I'm going to try to repeat that. Bjarne said that he had to make C++ go even faster than C, and he did it by doing a lot of weird stuff around the semicolons and the commas. Man, I'm butchering this. Sorry, Bjarne. All right, other questions?
We have a microphone for other questions now, which came just late enough. Sorry.
Great.
I was just curious. I really like the idea of like speculative syscall execution. That sounds pretty awesome. One thing I'm kind of curious about though, like, so when it comes to IOU ring, like I'm wondering whether or not any of the other major platforms are implementing anything kind of similar, because obviously like the standard usually exists above a level when it comes to like individual architectures and their capabilities. So I was just kind of wondering how you see those things mixing together and whether or not, you know, this is kind of where the industry at large is heading and whether or not other platforms are giving similar capabilities.
Yep. Not that I know of, but this is a relatively recent development. I would be very surprised if they're not at least looking very closely at this. But yeah, it's a good point.
So engineering is all about trade-offs. I was wondering what the advantages of using the human computers are over using the electronic computers.
The advantage of using human computers is cute photographs.
So as the computer gets more and more efficient at arithmetic, the value of each bit of arithmetic goes down. In particular, the ability to do stuff that you can kind of throw away or that is not very valuable, that gets cheaper and cheaper and cheaper. So I guess my question for you is, why would you want to avoid these syscalls and do these in the kind of a complicated higher level way at IOU ring, when instead what we could do is allow ourselves to do a lot of really cheap throwaway arithmetic and a lot of really cheap assembly instructions to do this simple thing directly? Because there's nothing fundamentally expensive about a syscall. Pre-Spectre, a syscall transition costs you about 20 nanoseconds. Like the assumption is it's like 10 mics, and that's just not true anymore. Like it hasn't been for a decade. So why can't we do the speculative execution that you want at a lower level with the more directly written code?
I don't know. Maybe we should. Yeah, I'd love to know an answer to that question.
Someone just asked about things like IO ring. On FreeBSD, there's something called KQ. So, and it existed before IO ring. The idea of a queue. It doesn't have some of the nice features like you mentioned of IO ring, but if you're interested, there's a BSD user group in the city.
Nice. All right.
I have one, if
Oh.
that's okay.
Okay.
So it feels like we're kind of standing on a tower of the as if rule all the way up. And I guess I want to know for you and really for everyone here, how many times in your career have you had to peak below the level that you're working at to solve a problem or to debug something, for example, to know that the registers are a lie to solve some sort of problem?
I got to say that it's, for me, it's come up once in my career when I had to optimize some code to make it as fast as it possibly could go. And that's where I was looking at the assembly level, not so low that I had to care about this pipelining stuff. That's just insane. But I would presume that there are some people out there that think that computers are not fast enough. And so they have to deal with this. Yeah.
But I think the most important lesson of this whole process is that the work of optimizing your code nowadays cannot any longer be in terms of reasoning about what the computer is doing, because it is literally impossible to reason about what the computer is doing. Like the most important lesson I think is that the only way to optimize is by benchmarking and that's it. Like don't try to reason about what the computer is doing.
All right. Oh, one more comment.
When I teach my students, I teach at Columbia now. When I teach my students, I always teach them to measure things. And I always tell them that our intuition doesn't apply. The shocking thing is that third-year students on average have never measured anything in their academic career.
So I have quite a few answers to your examples, anecdotes to your question about looking under the, so you can ask me later, I'll give you more. But one interesting one would be with upgrading a compiler, the newer compiler, the better compiler, would emit larger binaries because it had added more features to the way debugging happened. And for various reasons, that was not something we were able to ship in our environment. So to look under the hood, you have to be like, okay, well, even beyond what David's talking about, the compilers are injecting a bunch of extra stuff just in case some other program might be interested to learn about what's happening in the state of your program. And again, that's under the hood. You have to learn about dwarf and elf and all kinds of arcane things that none of us really look into. It's actually a fairly specialized skill even within our industry to understand what happens there. That's one example, but I got a bunch more if you want them. Basically, anytime your compiler breaks and doesn't work on your code, it's some sort of like abstraction breaking almost every time, especially with like a compiler like crashing or something like that.
All right. Well, with that, we're going to close and hope everybody can hang around for fellowship afterwards. And great to be here. Great to see you all.